Okay, let's dive right into this explainer and find the back door into passing one of the absolute most misunderstood topics in Cambridge computer science. We are talking about bus width. Examiners consistently report that understanding the factors affecting computer performance is literally one of the most challenging areas for students across the board. It doesn't matter if you're building your foundational knowledge on the IGCSE courses, like syllabuses 0417, 0478, 0983, 0984, or 2210, or if you're sitting the advanced AS and A-level 9618 papers. This concept right here, it can be a notorious grade killer. But today we're changing that. We're going to completely decode the examiner's mark scheme. We're going to take those incredibly complex architectural concepts, the CPU, memory, data buses, address buses, and turn them into an actionable, repeatable system. Basically, we are going to learn how to work smarter, not harder.
So here is our roadmap for today's session. We'll kick things off with a challenge, then move into the core principles you absolutely need to know. After that, we'll break down the procedural framework, look at some crucial examiner warnings, and finally, we'll build your personal success blueprint.
All right, Section 1, the challenge. Why do top students who study for hours and hours, still lose marks? Let's explore why working harder doesn't always translate to working smarter in the exam hall.
Now, what's really interesting about these two approaches is that it sets up the exact problem we see constantly. The assessment framework for Cambridge Computer Science prioritizes analytical depth over superficial breadth. Simply writing down everything you've ever memorized about a computer's architecture is a guaranteed way to just run out of time. Let's look at two students, Alex and Sam. First, let's evaluate Alex. Alex has essentially just vomited theory onto the page without any real analysis. In response to a really complex question about performance bottlenecks, Alex wrote that a bus width is the number of parallel wires, a data bus carries data, and so on. Now, these are true facts, sure, but there is zero analytical depth. Alex missed the context entirely. Now consider Sam's approach. Sam rushed. Sam just wrote that a wider bus makes the computer faster because it moves more data. Sam has completely missed the command word requirements and skipped showing any kind of logical reasoning or working. Both of these approaches are going to drop massive marks, and it's because they lack strategic application.
Before we fix this, you need to know there are three distinct cognitive domains that examiners are actively targeting: knowledge and understanding, application, and analysis. Think of this like a giant pyramid. At the very base, you have your knowledge. That's simply knowing that a 64-bit data bus can transfer 64 bits simultaneously. The next level up, that's application. That means applying that fact to the specific scenario given to you, perhaps calculating the data transfer rate given a specific clock speed. But the peak of the pyramid, where the top grades actually live, is analysis and evaluation. This is where you have to explain exactly why a wider data bus reduces the number of fetch cycles needed for complex instructions, and how that interacts with the clock speed to prevent the CPU from idling. That's the sweet spot.
Moving on to Section 2, Core Principles. Hacking the command words. The foundational rule of approaching any past paper is understanding that the command word dictates your entire approach. But before we reveal this strategy, subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. And hit the bell icon right now. Okay, let's get into the framework.
If an exam question asks you to evaluate bus width performance, you can't just guess. You must use a structured, evidence-based reasoning framework. We call this PEAL. Point, evidence, explanation, link. This framework brilliantly illustrates how top students structure their answers. Let's apply this to a 64-bit architecture scenario so you can see it in action. First, your point. Increasing the data bus width from 32 to 64 bits improves system performance. Simple enough. Then, your evidence. A 64-bit bus transfers 8 bytes of data per clock cycle, whereas a 32-bit bus only transfers 4 bytes. Next, your explanation. This means if a CPU needs to fetch a 64-bit floating point number from RAM, the 64-bit architecture can do it in a single fetch cycle, while the 32-bit architecture requires 2 separate cycles, literally doubling the retrieval time. Finally, your link. Therefore, widening the data bus reduces memory bottlenecks and decreases overall instruction execution time. Do you see how powerful that is? This framework forces the analytical depth that examiners are desperate to see.
Which brings us to Section 3, the procedural framework, algorithmic thinking in exams. So, the crucial takeaway here is that tackling bus width requires step-by-step decomposition and systematic processing.
You really need to treat the exam question itself like a piece of code that needs compiling. Algorithmic thinking means you don't just pick up your pen and start writing immediately. Instead, you execute a standardized sequence. Step 1. Identify the key elements. You scan for the command word and you circle the specific variables given to you, like clock speeds or cache sizes. Step 2. Apply relevant principles. You recognize that performance is a function of clock speed multiplied by bus width per cycle. Step 3. Execute analysis. This is where you actually do the math. Step 4. Verify if the answer makes logical sense. And Step 5. Present your final answer using that Peel structure we just talked about. This 5-step algorithm guarantees you won't miss any of those crucial mark-earning details.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. We've helped thousands of students improve by 2-3 grade boundaries. Join them right now by subscribing to @acetheexams_IGCSE and turn on all notifications so you never miss our weekly exam strategy sessions. Okay, listen closely, because this next point is absolutely crucial. As the Cambridge Principal Examiner reports explicitly state, students lose marks by not showing working. Even if your final answer is wrong, method marks can save you. We call this the method mark strategy. It's your insurance policy. So many students try to do the math in their heads. They make a tiny arithmetic error under pressure, and boom, they score 0 out of 3. If you just write down your formula, for example, data transfer rate equals width divided by 8 multiplied by clock speed, and plug in the numbers clearly, the examiner can see your logic. Even if you mess up that final multiplication, you still get method marks for applying the correct principle. Always, always show your working.
The difference between an average grade and top-tier performance isn't just about natural talent. It is entirely about having access to the right strategies and practicing them consistently. The data shows that students who rigorously implement these structured frameworks, the ones who show their working and analyze edge cases, can improve their outcomes by up to 2 to 3 whole grade boundaries. That is a massive jump.
Let's move into Section 4. Examiner warnings, the top 3 traps. Let's evaluate exactly where things go wrong for most students by looking at direct feedback from the principal examiner reports.
When evaluating algorithm quality and bus width performance, you absolutely must systematically identify time complexity, space complexity, and those really tricky edge cases. For instance, if a question asks how upgrading an address bus from 16-bit to 32-bit affects the system, you have to think in these dimensions. Let's break it down. For space complexity, a 16-bit address bus can only access 65,536 memory locations, right? But upgrading to 32-bit exponentially increases the maximum addressable memory to a whopping 4 gigabytes. You must state those exact numbers. For time complexity, if your data bus is wider, you fetch more data per clock tick, which drastically reduces execution time. And then, edge cases. Think about this. What if you have a 64-bit data bus but your software is only compiled for 32-bit operations? Well, the system cannot utilize the hardware efficiently. These are the specific boundary conditions that examiners are just dying to see in your answers.
You've got to avoid these 3 fatal flaws: relying on superficial breadth instead of analytical depth, ignoring boundaries, and failing to use comparative connectives when evaluating alternatives. Let's do a quick find the flaw exercise right now. Imagine a student writes this: "The system is slow, so increasing the bus width will fix it and make it faster." Can you spot the flaw? The flaw is that it is entirely too vague. It lacks any specific technical details. A top-tier, grade A answer would say something like, "The current 16-bit data bus is creating a bottleneck because the processor operates at a high clock speed but is starved of data. Widening the bus to 32 bits allows a full 32-bit instruction word to be fetched simultaneously, alleviating the bottleneck." See the difference? Furthermore, generic answers get heavily penalized. If the exam question is specifically about an embedded system inside a washing machine, your answer must reference the washing machine's specific memory constraints. Don't just give a generic textbook definition. Context is king.
All right, we have arrived at Section 5, your success blueprint. Putting it all together, we are now going to synthesize all these rules into a cohesive system that practically guarantees top marks for practical application and algorithmic design.
This right here is the exact strategy you need to practice until it becomes absolute second nature. Let's recap the 3 unbreakable rules. Rule number 1, command word decoding. Always start by circling the command word and extracting the scenario data from the prompt. Rule number 2, Peel framework application. Never write a paragraph without a clear point, technical evidence, a logical explanation of the performance impact, and a link back to the question's core scenario. And rule number 3, time management and method working. Allocate your time based strictly on the marks available, and physically write down your logical steps and your formulas to secure those method marks, even if your final calculation goes completely awry. This matrix is your ultimate weapon in the exam hall.
Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly explainer sessions. So here's your final reminder. Subscribe to our YouTube channel Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @acetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this explainer with a study partner. Ace the Exams. Your Cambridge success starts here. Keep practicing, keep applying the blueprint, and you'll be well equipped to completely hack any question the examiners throw your way.